Hello, welcome to the lecture 13 of the course Transportation Network Analysis. So, in the last class, we were discussing about this L exchange method to solve the traveling salesman problem. So, today we will continue that discussion. So, let us define this L exchange method. So, an improving L exchange is an L exchange that results in a tour whose total length is smaller than the total length of the original tour. Okay. And a K of procedure starts from an arbitrary feasible tour and it successively does various L exchanges such that L is less than or equal to K, so that it keeps generating these tours of smaller and smaller length successively. And this procedure terminates when no improving L exchange is found for all L less than or equal to K. Okay, so for example, if K is specified to be say 3, so then we will have L less than or equal to 3 only, and every time in each iteration of this algorithm we will be implementing various L exchanges so that we get a tour which is smaller than the previous tour. So, let L be the length of the tour which is generated by a 2-opt algorithm. So, here we are supposing that K is equal to 2 and let L star be the length of the optimal tour. Then if the triangle inequality is satisfied, then for all instances of the traveling salesman problem, we have L by L star less than or equal to 4 root n, where n is the number of nodes that are present in the graph. So, this is important that the triangle inequality should be satisfied, and only if this is satisfied among the link weights that are given to us in that traveling salesman example, then only this results hold. Okay. Now, we will not be discussing a proof for this here because of the shortage of time, and we need to focus on other important topics as well. But just to tell you that important point here is that this 4 root n is a function of n, which is the number of nodes that are present. So, if n becomes large, then this ratio will also increase, and therefore, the guarantee that we will have of the length that is obtained by this 2-opt algorithm versus the optimal length, which is L star, the gap between this guarantee will keep increasing. Okay. For example, if say n is equal to 4, okay, so then we get L by L star is less than or equal to 4 times 2, which is equal to 8. Whereas if n is equal to 16, we get L by L star less than or equal to 16. Okay. So, you can see that here in the first case where n is equal to 4, this result will guarantee that for all instances of the TSP, that is for all examples of the traveling salesman problem, the length of the tour that you obtain will be less than or equal to 8 times the length of the optimal tour. Whereas in this case here, when n is equal to 16, this result will guarantee that the length of the obtained tour will be less than or equal to 16 times the length of the optimal tour. So, therefore, this guarantee becomes looser as n increases. Okay. And this is in contrast to the constant factor approximation algorithm that we had seen before for the traveling salesman problem, the one where we were using this minimum spanning tree and then we were using this pre-order walk. So, there the approximation ratio was 2 there. So, that did not change with the size of the problem, but here this changes. However, this is still better than not having any guarantee in terms of what length of tour will be obtained by a particular algorithm. So, this is saying the same thing which I mentioned. So, the upper bound on L by L star in the last result keeps increasing as the number of n nodes n increases. Thus, unlike the MST based algorithm that offered a constant upper bound on L by L star, this 2-opt algorithm does not offer a constant bound. Okay. However, it can happen that for some examples of the traveling salesman problem, this 2-opt algorithm might give you a better solution as compared to the MST based algorithm and vice versa. Okay. So, both of these two algorithms are useful, and therefore, we discussed both of them here. Okay. So, we will use this term approximation algorithm for a polynomial time algorithm that gives a guarantee on the value C that is obtained by the algorithm with respect to the optimal value C star. okay, and this has to happen for all the instances of the given problem. So, mathematically what it means is that suppose rho n is the approximation ratio here, where rho n is greater than equal to 1. Now, n is a parameter that is representing the size of the problem. For example, in the travelling salesman problem, n can be the number of nodes, and the following result holds that maximum of C star by C and C by C star is less than or equal to rho n. Okay. Now, you might be wondering why there is a max present here. This max is present because this definition of approximation algorithm holds for both maximization and minimization problems. Okay. For example, when we were discussing this travelling salesman problem, that is a minimization problem because we want to minimize the length of the tour that is obtained. So, there we were having this guarantee that L by L star is like either less than or equal to 2 in the case of MST based algorithm, or it was 4 root n if it was the 2 opt algorithm. So, these 2, 4 root n, these are the approximation ratio. Okay. And since it is a minimization problem, the travelling salesman problem, the length of the tour that is obtained from these algorithms cannot be shorter than the length that you obtain from the optimal tour, and that is why we had this L by L star is less than or equal to either 2 or 4 root n depending upon which algorithm we are talking about. However, if we are talking about a maximization problem, so then if we have an approximation algorithm, then the value that algorithm will give, suppose that value is L, so then that value will be lesser than the optimal value, and therefore, in that case we will be interested in this kind of ratio L star by L, and this will be less than or equal to some rho n. For example, if rho is 2 or it can be 3 and so on. Okay. So, that is why we have a max written here. So, depending upon whether the optimization problem that we are focusing on, if it is a maximization or minimization, either one of these two terms will be larger, and accordingly this definition will be satisfied. Okay. So, just to go through this definition again of the approximation algorithm, the important terms here are that this approximation algorithm first of all should be a polynomial time algorithm, okay, and it gives a guarantee that for all the instances of the problem, okay, that is for all the examples of this problem that you are focusing on, this algorithm will give a guarantee on the value that is obtained with respect to the optimal value C star. Okay. Now, for the algorithms for which no such guarantees are known, they are called heuristic algorithms. So, we will be referring to them as heuristics, and sometimes in some books and so on, there is an alternative usage that refers to all the algorithms other than the optimal ones as heuristics. For example, this algorithms that we have seen for solving the travelling salesman problem, the 2 until now, when the triangular inequality is satisfied, the 2 approximation ratio and the 4 root n. So, these are approximation algorithms because they are not guaranteeing that you will get the optimal solution, but there is a guarantee on the value that this algorithm gives as compared to the optimal value. Okay. But then we have these problems like minimum spanning tree, shortest path problem, for which we know the optimal algorithms. For example, for the minimum spanning tree we had the Prim's algorithm, Kruskal's algorithm, and for the shortest path problem we have the Dijkstra's algorithm. So, in some literature it is referred to as all the algorithms other than the optimal algorithms as heuristics, but we will not be going into that notation. We will be having 3 kind of categories of algorithms. One is the optimal algorithms which guarantee optimal solution for all the instances of the problem. Then are these approximation algorithms which give a guarantee on the value that is obtained with respect to the optimal value, and then there is this heuristic algorithms for which no guarantees are known. Okay. So, until now we were discussing about the travelling salesman problem. Now, let us focus on the vehicle routing problem, which is an extension of this travelling salesman problem, and this vehicle routing problem arises very frequently in the real world. We had first seen this in the introduction of this course. So, let us go into the details of this problem and how to solve it. So, this problem arises frequently in logistics to solve problems such as how to dispatch a fleet of vehicles in order to minimize the operating costs or other objectives. Okay. So, you can see that there is a diagram here, there is a depot node here, and then there are these several of these circles of different colors. Each of them are representing different customers and their respective locations. So, the objective is that we want to dispatch these goods that are available at this depot node to these customers who want them. But the issue is that the vehicles that are available to dispatch cannot carry an infinite number of goods, and therefore there is a limit on the amount of goods that a particular vehicle can carry, and therefore we cannot have a single loop where a vehicle travels all of these circles and then comes back to the depot node. And therefore, in this case we might require these multiple tours which will be visited by separate vehicles. So here this is one tour which is consisting of these blue circles. This is another tool which is consisting of these green circles, and this is another tour which is consisting of the red circles here. So every tour is being handled by a single vehicle. So this is the problem that we want to focus on. So the most basic version of the vehicle routing problem, or in short also called VRP, is the single depot capacitated vehicle routing problem, and this is also called CVRP in short. Okay, so here we have a single depot, that is what the first term is saying, and the second thing is that we have these capacitated vehicles, that is there is a limit on the total quantity of goods that each vehicle can carry. Okay. So in the CVRP, or this capacitated vehicle routing problem, a set of customers are to be served by a fleet of identical vehicles of limited capacity. Okay. So we have these vehicles which are all having identical capacities, and all of these vehicles are initially located at a given depot node. The objective is to find a set of routes for the vehicles of minimum total length. Okay. Note that this travelling salesman problem is an instance of CVRP when there is a single vehicle that has infinite capacity. Okay. So if we had a vehicle that can carry infinite amount of goods, then this CVRP will become equivalent to the travelling salesman problem. Okay. Now, since we had seen that, or we had discussed at least that this travelling salesman problem is NP-hard problem, that is, it is not possible to solve this problem optimally in polynomial time. Therefore, since this vehicle routing problem is also an extension of this travelling salesman problem, so this vehicle routing problem is even harder than that, and therefore by the same argument we can extend that this vehicle routing problem is also unlikely to be solved in polynomial time optimally. Okay. So therefore currently there are no such algorithms to solve this vehicle routing problem optimally in polynomial time, and therefore we will be looking at some other ways to find the solutions of this problem. Okay. So in this capacitative vehicle routing problem, we will be considering a case where this problem that we have CVRP with equal demands. Let us see what this means here. Suppose a customer requests W units of product. Okay. And also suppose we allow this load to be split between more than one vehicle. Okay. That is, this customer is fine on getting several deliveries, all of which together sum up to the total load that is requested. Okay. So for example, if suppose I have ordered say 10 units of a particular item, that is suppose 10 copies I have ordered, then in this version of the CVRP where we are saying CVRP with equal demands, I am fine with getting multiple deliveries such that, for example, the first delivery might provide me 3 copies of that item, the second delivery might provide me 4 copies of the item, and the third delivery provides me again 4 copies of the item. So since it has to add up to 10, so suppose the first delivery provides me 2 copies of this product, the second one provides me 4 copies of the product, and the third one also provides me 4 copies of the product. So all of them will add to total of 10. Okay. So this is the main assumption of this capacitated vehicle routing problem with equal demands. So since we are allowing this assumption that every customer is fine with getting multiple deliveries for whatever amounts of product that they ask for, so therefore you can view that the demand for W units as W different customers, each requesting 1 unit of product located at the same point. Okay, this is important here. So we are saying that since everyone is fine with getting these products in form of multiple deliveries, so we can think that if a person is suppose asking 10 copies or 10 units of a particular product, then we can assume that actually there are 10 customers there and each of them is asking 1 unit of that product. okay, but all of them are located at the same point or location. So the capacity constraint can be viewed simply then as the maximum number of customers in this new problem that can be visited by a single vehicle. In this new problem, we mean that we have now converted this original problem where every, suppose customer was asking finite amount of a particular product, and for every such customer we have transformed this problem where we have, suppose that customer asks W units of the product, then instead of one customer there are W such customers at the same point, but each of them is asking for 1 unit of that product. Okay. So in this new problem, now we can think that since every vehicle that we have with us has a capacity of the number of items it can carry. So therefore, in this case, since every person is now only asking for a single unit of a particular product, so therefore, assuming that every customer is asking for the same type of product but different quantities, so therefore this problem then becomes that the capacity constraint, that the single vehicle should then not carry more than the maximum number of customers it can do at a time. For example, if a particular vehicle say cannot carry more than 20 units of product, so then it is equivalent to saying that since every customer now in this transformed problem or the new problem is asking for 1 unit of product, so now this vehicle or this truck should not visit more than 20 such customers. Okay. So let us represent this capacity of this truck by q, which is greater than or equal to 1. So we will be assuming that q is a positive integer. So thus if we allow this splitting of demand, there is no loss of generality in assuming that each customer has the same demand, namely 1 unit, and each vehicle can visit at most q of these customers on a route. Okay, so this is kind of summing up this discussion that I mentioned, that now that everyone is fine with getting multiple deliveries of the product that they are asking for, so therefore there is no loss of generality in assuming that each customer now has the same demand of 1 unit and each vehicle will now visit at most q of these customers on a route, because every person now or every customer is now asking for a single unit only. So this model is called CVRP with splitable demand or eCVRP. Here E in eCVRP is standing for equal, that is every customer is asking for same amount of a product, which is 1 unit. Okay. So let us look at an algorithm to solve this problem. This algorithm is called iterated tour partitioning. So in this we consider a feasible tour for the TSP, okay, and this need not be the optimal tour. So what it means is that in the beginning we will be starting with a tour that visits all of the customers and then comes back to the depot node. Okay. So therefore it is a feasible tour because it visits all of the customers and it comes back. Okay. But it need not be the tour does that in the least time or least distance, okay, or that has a least length. So we just need to start with a tour of this traveling salesman problem. Then this iterated tour partitioning, ITP, is to partition a feasible TSP tour into segments such that each segment of customers is served by a single vehicle. Okay. So when we are applying this iterated tour partitioning, before that we have transformed this original problem that we have into the problem where now every customer is only asking for 1 unit of the product. Okay. So therefore we will be considering, we will partitioning this tour that we start with into multiple segments such that each segment will be corresponding to a single vehicle. Okay. And you can then think that the number of customers in each segment then should not exceed the capacity Q. Okay. Because here in this transformed problem every customer is only asking for 1 unit of the product. Okay, that is each segment has no more than q points. A point is a customer with unit demand. Okay. So let us consider an example to illustrate this ITP algorithm. Suppose q is equal to 2. Then the following figures will illustrate the feasible solutions that would be formed in this example using the ITP algorithm. So q is given to be 2. So every vehicle cannot carry more than 2 units of this product, and since in this transformed problem every customer is only asking for 1 unit of a product, so therefore every vehicle will not be able to visit more than 2 customers at a time. Okay. So this is the example problem. Here we have the depot node in the middle, which is shown by x0, and we have these 6 customers represented by x1 till x6 here. So we are first showing this algorithm to get an idea of how it works. So what we do is that, see, initially what we had is we had a tour given to us. In this tour, this x0 node, which is the depot node, is visited first, then the x1 node is visited, then the x2 node is visited, then the x3 node is visited, then the x4 node is visited, then x5, and then x6, and then we finally come back to the depot node. Okay, this was the tour that we started with. Okay, and then what we do here is that in this tour we first provide a single customer to the first segment. Okay, so here you can see that we have a single segment here, that is a vehicle will go from depot node to this node x1 and then it will come back. Okay, so this is one segment. Now leaving this first segment, now the second segment will have 2 units, that is 2 customers it will be going to. So it goes from x0, this vehicle, then it goes to x2, x3 and then back. Okay, now here we can kind of assume that it's suppose undirected graph, so we can as well just go from x0 to x3, x2 and then x0 back again. Okay, then the next segment consists of again 2 customers. Okay, so this vehicle will now visit in this way, and finally since we just have one more customer left here, so the last vehicle will just visit it and then come back. Okay, now this is one solution of the problem. In the another iteration of this algorithm, what we will do is that we will be adding one more customer to this first segment that is there. Okay, and then we will be clubbing together these 2 customers x3 and x4, and after that we will be clubbing together these 2 customers x5 and x6. Okay, and now that there are no more customers to club, so we stop here. And in this algorithm, this and this are the only 2 solutions that you obtain, because since q is equal to 2, so we cannot now add further x3 also with x1 and x2 in this first segment here. Okay, so that's why these are the 2 solutions that we get from this algorithm, and the solution which has the least length, that is the total length of going from depot node and then coming back in all of these segments, when you sum all of that, whichever one has the least, we will be selecting that solution. Okay, so in the next class we will be continuing this discussion of the iterative tour partitioning. Thank you.